Hi, I'm Rick Streacker, Packard's National Training Coordinator. Today we're going to talk about unit bearing motors. Now you may have heard them called watt motors, or maybe even cannonball motors. They're all the same type of thing. Now they get their name because when these motors first originated, there was one bearing inside of the motor. That's why we call it unit bearing. And an excellent design. The bearing was very, very stout, very hardy, and it also allowed for a lot of oil retention within the bearing system, which resulted in great life for these motors. Now the unit bearing is a sleeve bearing motor. Now when we look at these, you can see how there's something called end play. I'm able to move this shaft in and out of that motor. That's called end play. And with a sleeve bearing motor, it's important that there's end play in there so that when the motor heats, when it gets hot from the resistance in that winding, as it heats up, the washers that are in that will expand. And so if I don't have end play in there, and when the washers expand because of the heat that develops in a motor naturally, then that motor will become tight and it may not operate. So we have to have end play in a sleeve bearing motor. Now some of the newer designs no longer are using sleeve bearings. On the electronically commutated motors, for example, they use ball bearings because I don't want that rotor moving back and forth and perhaps interfering with the electronics or touching the electronics that are in the back of the motor. So we use ball bearings in the newer designs, but they look similarly to some of the designs that we've been using. So we might see them called watt motors more frequently now rather than unit bearing motors. Well, why are they called watt motors? When we look at these motors, they don't have a lot of horsepower to them. They're operating small loads, small fans. When I compare the size of the fans that I see in refrigeration with what I see in air conditioning, if I look at a condenser motor in an air conditioning system, that fan blade's going to be a lot larger. There's a lot more load on that. And so I need a stronger motor to do that. But on these unit bearing motors, the watt motors, we refer to them in watts because that's their output torque. And we refer to it as watts instead of horsepower because the amount of output torque is so small. So if I have a 2-watt motor, it's a lot easier calling it 2 watts rather than 1 373rd horsepower. There are 746 watts in 1 horsepower. And so in these particular motors, we refer to their output in a much smaller increment. That's a lot easier to talk about than if we were to use horsepower. So we see these watt motors go from 2 watts to 50 watts. So there can be a broad range of those. And we size them based upon the amount of torque, the amount of watts that we have on their output. So a 2 watt, a 4 watt, a 6, a 9, a 16 watt motor. So that refers to their output. And when we replace those, we want to replace them with one that provides that same amount of torque, that same amount of output, that same amount of wattage. So I'm looking for matching the watts when I replace those motors. I also look at the speed of the motor. Now the majority of the motors are going to be about 1550 RPM. So it's pretty typical to be able to find those motors with those speeds that are needed. But they operate at 1550 RPM typically. We might see some 1625 out there as well. The motors may come with a cord. Some may not have a molded cord set on it, but just leads that come out of the side of the motor. Sometimes the cord that comes out of the motor may have a plug on it, sometimes it doesn't. If we look at these particular motors, they have plugs on them. These plugs are typically referred to as Lyle plugs. And these that we have here on the table, we have two different Lyle plugs. This is called a straight plug. This is called a right angle plug. On this plug, the cords come up and then they come out at a right angle for the actual prongs on the plug. And that may be an important characteristic in terms of how those motors are mounted in a system. Speaking of mounting, we see different configurations in terms of mounting on these motors. Now it's possible on some of these motors, they may have feet, a foot pad for mounting the motor. Sometimes they don't. Sometimes they have more than just one combination of foot pads. They may have two sets of foot pads on them. And that just gives us the option to be able to mount them differently in different applications. In some of these motors, we may use a bracket, and that foot pad will allow that motor to attach to that bracket and then fit the proper height inside the condensing unit to make sure that the fan blade is centered. Sometimes these motors aren't mounted by foot pads, and they may be mounted through bolts on the back of the motor. Now this particular motor has 3 bolt holes in the back for mounting this to an application. This one has more than 3. When we look at this, we've got 1, 2, 3, 4, 5, 6 different sets of thread holes. It doesn't mean that all 6 of those holes are used when this motor is installed, but it gives you a flexibility so that you can mount this with different combinations of those holes. Maybe you only use 3 of the holes. Maybe you'll use 2, maybe you'll use 4. But it gives you the flexibility then to take one motor and use it in a number of different applications. On some of the new motors, some of the ECMs, we have multiple mounting holes in the back. We have double foot pads. And I could also mount this motor with bolts that attach to the front of this. So it gives you a lot of different options for mounting. The shafts on these, most of these are the same size shaft. But when you look at this motor, this is a little stronger motor. This particular motor is a 50-watt motor. That particular motor is doing more work. It gives me more output than what I see in these smaller motors. But because of that, that particular motor has a different size of shaft on it. Because it does have more torque, I don't want to take a chance on breaking a smaller shaft if something were to happen with this on the load when I'm trying to start it. So these motors have a little more shaft. It also supports the fan more sturdily when I have a bigger load on that. So we can see different shaft sizes based upon the type of application, based upon the amount of load that's going to the motor. These particular motors have a special device in the front of the motor that allows me to attach the fan blade through little nubs that allow the fan blade to attach easily to the motor and give that fan blade lots of support when it's operating. The rotation on these motors is generally, when I'm viewing the back end of the motor. Now, when you look at literature, it'll reference on most of these motors LE, lead end, because the leads come out the back end of the motor. So that means when I'm looking at the back end of this motor, my reference point is from this side when I determine the rotation. On this particular motor, it's a little bit different than what we see in condenser motors or blower motors. On the condenser motors and the blower motors, we'll refer to the rotation as either CW for clockwise or CCW for counterclockwise. But after that, we'll put LE if I'm viewing it from the lead end, or SE from the shaft end. On these motors, it doesn't say on that nameplate CCWLE. Well, why not? When I'm looking at the nameplate of this motor, I'm viewing it from this end. And so it says CCW. That's all it says. That means it's CCW from this end. So that particular motor would be going counterclockwise when I'm viewing it from this end. And that's an important distinction to make. On this particular motor, those leads are coming out of the middle. If I refer to the lead end, I might be confused a little bit. I may not be sure which end would be considered the lead end. To be consistent with these motors, we reference the rotation from the back end. But now, in literature, it would reference that rotation as OSE, meaning the reference point is when you're looking at the opposite shaft end, which would be this end of the motor. These motors are called induction motors, whereas these motors are electronically commutated motors. These are ECMs. Again, these are induction. When we replace any of these, we replace them based upon their wattage, their watts output, as well as the voltage that's going to the motor and the speed of the motor. So we use the same criteria. These operate a lot differently than these. And it's very possible that you might be able to use one of these motors to replace most of these over here that are induction motors. These motors, they're very specifically designed as something we call constant speed ECMs. And so regardless of the torque that I'm required to have, regardless of the load that I put on there, as long as that load is within the tolerance range of these motors, as long as I'm not overloading that motor or excessively underloading that particular motor, it's going to operate its load at the same speed, at 1550 RPM. So these motors can often be used then in multiple wattage requirements. I could replace a 2 watt or a 4 watt or a 6 or a 16 or a 25 with just one of these motors. Whereas with the induction motors, the replacement needs to match the wattage of the motor that was originally in there. So the ECMs allow us to cover a much broader range, and they're more efficient. And they improve the performance of my refrigeration system. When I'm operating one of these motors, they're about 30% efficient, whereas these particular motors are going to be closer to 65 or 70% efficient in their performance. So even though these motors might look a little bit different than these, they are designed to be able to fit as a replacement for these and improving the performance of my system. as a result of that. So Watt motors, they've been around a long time. These unit bearing motors, their designs are changing a little bit. Instead of the unit sleeve bearing that we've seen in there, we'll go into a ball bearing. But they perform at above the performance characteristics that we saw with these induction motors. So I hope that gives you a little bit of background and maybe a little bit of comfort when you're trying to select the proper replacement for these unit bearing motors, for these Watt motors. Well, we appreciate you being here at the Packard Academy today and hope you come back soon. Thanks so much.